All right, good morning, guys. We're going to go ahead and get started. So if you would like, please go ahead and start writing a short paragraph that explains why a triangle can only have one obtuse angle or only one right angle. You can pause the video as you do this, and then we'll go through some explanations with it. All right, so a triangle has a total sum for all of its angles as 180 degrees. It can't go past 180 degrees by definition, and we'll be proving this in a couple days. And for a triangle, it needs to have three angles. Again, that's why it's called a triangle. Tri meaning three, angles meaning angles, so it's three angles. An obtuse angle is greater than 90 degrees and less than 180, so it needs to be somewhere in there. And I know that a right angle must be 90 degrees. So if I take a right angle and an obtuse angle, and I'm going to take the smallest obtuse angle possible, 91 degrees, and I add them together, I have 90, the right angle, plus 91 degrees, the obtuse angle, plus our third angle, because again we need three angles, is equal to 180 degrees. Well, simplifying that down, that gives me 181 degrees plus x, my third angle, equals 180 degrees total within the triangle. Now, I know that x cannot be a negative angle, and I know that if it's equal to 0, it is also not going to be an angle. So therefore, this is not possible. I can't have 181 degrees plus another angle equaling 180 degrees. So this goes to show us that a triangle must never have two right angles or an obtuse angle and a right angle. If it's a right angle, it can have one right angle, one 90-degree angle, and the other two angles must be acute. Same thing with obtuse angles. I can have one obtuse angle, but the other two angles in that triangle must be acute as well. So again, we're never going to see a triangle with both an obtuse and a right angle inside of it, because it would no longer be a triangle. And in fact, I can draw a quick little diagram. If I have a right angle and then an obtuse angle, of course, this is never going to collapse and create a triangle, because again, this has to be obtuse, this has to be right, and there's only three angles within a triangle. Well, it's never going to create the third angle. So this is just an example of why we can't actually have this occurring. It won't actually create a triangle for us. All right, so today we're going to be covering 3.6 types of triangles. Our learning target is I can write two-column proofs involving overlapping triangles, isosceles triangles, and circles. Now, we covered circles in our previous videos, and we've also covered overlapping triangles already. So today we're going to focus exclusively on isosceles triangles, and we're also going to be focusing on defining each type of triangle, giving it a classification. So to get started, we're going to start with scalene triangles. A scalene triangle is a triangle in which no sides are congruent. So in a scalene triangle, nothing is congruent. All three sides are different measurements, and all three angles are different measurements as well. So a scalene triangle will have no two sides congruent and no two angles congruent. Nothing will be congruent in a scalene triangle. The next type of triangle that we have is an isosceles triangle. An isosceles triangle is a triangle that has at least, and that's very important that we know that it is at least two congruent sides. So if I have three sides congruent in a triangle, that is also isosceles, because again, I need at least two sides congruent. Two or more, two or three, because again, I can't have more than three sides. So in an isosceles triangle, there's very specific terms for each part of it. And I want to make sure that you guys know these terms, because we're going to be using them quite a lot. The first one that I want to talk about is the legs. The legs are the two congruent sides. It's what makes an isosceles triangle an isosceles triangle. So in an isosceles triangle, in this one specifically, we have DE, segment DE, and segment DF as our legs. Now, the legs meet with the base of our triangle. So that last side, the side that is not congruent to the two others, that is called our base. And our base is just our third side. It's the side that's not congruent. Now, on the base and where the legs meet, so where the base and the legs meet, we have base angles. So base angles are always connected to the base. And further, base angles will always be congruent in an isosceles triangle. So in our next video that we'll cover on Monday, you're going to notice that there is a relationship between the side length of a triangle and the opposite angle of the triangle. So as I can see, we have two legs that are congruent, and so our base angles are also congruent. And we're going to use that a lot in this chapter as we work on more isosceles triangles and more proofs. Now, the last part that we have is the vertex angle. The vertex angle is the only other angle. It's where the legs meet, and it's the only angle that is not a base angle. So the vertex angle is where the two legs, the two congruent legs, intersect each other. So go ahead and take a second and try and label each piece within triangle RST. You can just go ahead and draw arrows if you'd like, or you can go ahead and just list them all out once again. So first off, the legs of triangle RST. Well, those are the congruent pieces. So we have segment RS and segment RT. Next, our base angles. Well, our base angles are always on the opposite angle of the side. So if I'm seeing that these legs are congruent, well, the angle opposite this side would be angle T. So angle T and angle S are our base angles. Meanwhile, the only other angle that's left is our vertex angle, angle R, and that leaves our base as ST. And that makes sense because that's where both of our base angles are found along our base. So now we have triangle RST all labeled up. And again, you're going to see lots of different types of isosceles triangles. You'll see some isosceles triangles that are right triangles. And that's perfectly fine. You can see that we'll have a right triangle and an isosceles, and if that's happening, that means that both my base angles would be 45 degrees. Because again, 180 degrees total, I use 90, which means I have 90 remaining between two congruent angles, meaning both must be 45. Again, very important that you guys memorize each of these terms because I'll start saying them in our lessons to make sure that we're going through this stuff. But in problems, they may also say the vertex angle of this triangle is 48 degrees. Find the two base angles. And you'd have to be like, okay, well, the base angles will be a variable x. Since they're both the same, it'll be 2x plus 48 equals 180 degrees. And then from there, you would just solve for x, which would give you your base angles. So again, that's why it's important to know these these terms, is because we're going to be using them all the time. And if you're not sure what we're talking about, you won't know what you're trying to solve for. So again, spend a little bit of time memorizing these, knowing where to find them, and knowing what they are. The next term that we have, the next type of triangle that we have, I don't want to forget this. Let me go ahead and get out of there and jump back in. So base angles are always congruent. So they will always be congruent to each other in an isosceles triangle. Likewise, the legs in an isosceles triangle will also always be congruent. So it's important that we know this because it allows us to know that two sides are always congruent or two angles are always congruent. And that's going to help us a lot in our proofs. All right, so the last type of triangle that we have is an equilateral triangle. And I say this is the last one because we're going to see another one in just a bit, but it's important that we know that these next couple triangles are going to be related to each other. So an equilateral triangle is a triangle with all sides congruent. Now, this is in the name. Equilateral. Equal meaning the same. Lateral, in medical terminology, lateral means side. So this is really an equal-sided triangle, meaning all sides are going to be equal to each other. And keep in mind that relationship between the legs and the base angles of isosceles triangles, because that doesn't change here. Because if I'm looking at this equilateral triangle, is it also isosceles? Is this triangle isosceles? Well, if we go back to the definition of an isosceles triangle is a triangle with at least two sides congruent. Well, this has three sides being congruent, which is at least two. So yes, this is an isosceles triangle. Well, wouldn't that mean that the base angles are also congruent? Well, how do I know which side's the base and which sides are the legs? Well, wouldn't that just mean that all angles are congruent? Yes. And this leads us to our next triangle, an equiangular triangle. An equiangular triangle is a triangle in which all sides are congruent. All angles are congruent. And again, that's in the name. Equal, meaning equal. Angular, meaning angles. Equal angle triangle. So again, these two triangles are extremely similar. And you may be like, well, I kind of saw the equiangular triangle over here. Well, that's absolutely true, because an equilateral triangle and an equiangular triangle are the exact same triangle. In fact, if a triangle is equilateral, then it's also equiangular. And if a triangle is equiangular, then that means that it's also equilateral. So these are used interchangeably. And again, both of these are isosceles. Both are isosceles triangles. But if they asked me to define these or to classify these, I would go with the most exact classification as an equilateral triangle or an equiangular triangle. I know that these are both isosceles, but if they asked me for the classification, I would use their proper names, the most exact one. So again, these two triangles are the exact same type of triangle. They just have different names. And because they have different names, they give me different information when it's given. So if I'm given an equiangular triangle, I know all angles will be congruent, which then I can use in my proof to say that all sides are congruent. So again, we'll be using these as we go through. It's very important that we know these just so that we can use them down the road. All right, next up, we're going to have classification based upon angles. So an acute triangle is a triangle with only acute angles, meaning all of the angles in this triangle are acute. Now, if you recall, an acute angle is between 0 degrees and 90 degrees. Now, you may see this symbol here and you're not sure what it means. This symbol is just the Greek letter theta. And theta is used exclusively for angle measurements. So it's just saying my angles need to be between 0 degrees and 90 degrees. And again, it's important that we notice that they are not equal to those angle measures. They're just going up to that angle measure. The next type of triangle that we have is a right triangle. And it's very important that we get all the terminology in this and memorize this as soon as possible, because we're going to be working towards HL in just a little bit. And it's very important that we know all these different sides of a right triangle when we're dealing with HL. So, a triangle with one of the angles being a right angle, meaning 90 degrees, is a right triangle. Now, it's also important that we note the other angles must be acute. So these other angles here, these angles must be acute angles. If they're not acute angles, then this triangle will not be a right triangle. It goes back to that warm-up that we did, showing that if we have more than two acute angles and a right angle, it no longer closes into a triangle. And if I have two right angles, then it looks like this. So obviously that's not a triangle either. Our two sides don't meet at the end. So again, I can't have two right angles. I can't have two right angle and an obtuse angle. I must have one right angle and two acute angles. Now, along with that, let me go ahead and get out of this real quick and jump back in. The first definition that we have is the hypotenuse. The hypotenuse is often given the variable c. And in fact, the hypotenuse is the only one that has c as the variable in a right triangle. Now, to find the hypotenuse, it's the side opposite the right angle in our triangle. So if you're having trouble identifying where the hypotenuse is in a triangle, find your right angle and make an arrow out of it. That arrow is pointing right at my hypotenuse. And again, I can see that in this other triangle as well. If I make an arrow out of my right angle, it's pointing right at the hypotenuse. So you should always be able to find that hypotenuse just by creating that arrow. And we'll be doing this a lot once we get into trigonometry next semester. Now, the next type that we have, the next piece of this, is the legs. The legs are given the variables a and b. So it doesn't matter which leg gets A and which leg gets B. It does matter that the hypotenuse is C though. So again, the hypotenuse must be C. So the legs are the segments attached to our right angle. Both the legs will touch the right angle. And they always intersect each other at 90 degrees. So again, I can say that segment AB is little a and segment BC is little b. Or I can say segment AB is little b and segment BC is little a. Again, it doesn't matter which segment gets A and B, which leg gets A and B. What matters is that our hypotenuse is the C variable. Now, the last thing with this is Pythagorean's theorem. Pythagorean's theorem is one of the most famous geometric theorems that we have. It is a squared plus b squared equals c squared. This is used exclusively for right triangles, and it allows us to find any missing side length of a right triangle. So if I have two sides of a right triangle, I can use Pythagorean's theorem to find my third side. Now, Pythagorean's theorem was founded thousands of years ago by the ancient cult of Pythagoras. And it's very important that we memorize this one because we'll use it all the time. It's used very often in construction even, because obviously if I'm putting up a wall, then I need to have a right angle. And if I'm building that wall and it's going to be extremely long, then I need to have some scaffolds to hold that wall up. So using right triangles, we're still able to use right triangles for our construction and building homes, building buildings. It's used a lot. So make sure that you know Pythagorean's theorem. You're going to see some problems with it in the future, and it's good to start memorizing it now. Now, I told you guys that we need to know each of these terms because in one of our future videos, in a couple videos from here, we're going to have a new triangle congruency theorem. That is HL. And HL can only be used with right triangles. Well, what do you think HL stands for? HL will stand for hypotenuse leg. So in the next week or so, if you notice that you have a hypotenuse and a leg in a right triangle congruent to a hypotenuse and a leg in another triangle, then we would say those two triangles are congruent by HL. And we'll be covering this more in depth next week, so just keep that in mind. It's something that you should keep an eye out for, but that's why it's important for you guys to be able to know where these are located in a triangle and what they actually are. The last type of triangle that we have is an obtuse triangle. An obtuse triangle is a triangle with one obtuse angle. And again, the other two angles must be acute. The other two angles must be acute. So again, our obtuse angle must be between 90 degrees and 180 degrees. And then our other two angles need to add with our obtuse angle to be 180, meaning that they need to be acute angles. They need to be less than 90 degrees in order to do that. So again, we have one obtuse angle, and the other two angles are acute. All right, let's go ahead and try a practice problem out. So go ahead and pause the video if you'd like, try this problem out, and then we'll be going through it together. So for this problem, we're given AB is equal to x plus 3, AC is equal to 3x plus 2, and BC is equal to 2x plus 3. The perimeter of triangle ABC is equal to 20, and we want to show that triangle ABC is scalene. So pause the video, try this one out if you'd like, and then we'll continue on. The first thing that I'm going to do here is I'm going to draw my triangle ABC, and I'm going to list all my sides. So I have AB as x plus 3, BC as 2x plus 3, and AC as 3x plus 2. Now, I also know the perimeter, the distance around this figure, is 20. So I can go ahead and say that if I add up each of these segments, it will equal 20 in length. So I now have AB plus BC plus AC equals 20. Well, combining like terms, x plus 2x plus 3x will give me 6x. 3 plus 3 plus 2 will give me positive 8. So I now have 6x plus 8 equals 20. I start solving for x. Subtracting 8 from both sides, I get 6x equals 12. Then dividing both sides by 6, we get x equals 2. Well, if I want to show that triangle ABC is scalene, what do I need to do? Well, I would need to show that each side is not congruent. And to do that, I would need to plug x back in. So plugging x back in, I get side length AB is 5, side length BC is 7, and side length AC is 8. And since none of these numbers are the same, they're all different, triangle ABC is scalene. All right, let's go ahead and try out our next one, our final problem for the day. Go ahead and take a minute, pause the video, and write out this proof, draw it up, and then we'll be going through it together. We're given angle 1 is congruent to angle 3, angle 2 is congruent to angle 4, and PJ is congruent to PO. We want to prove triangle KPM is isosceles. So here's triangle KPM. If we want to prove that this is an isosceles triangle, that means that we need to prove that at least two sides of the triangle are congruent. Well, looking at this, I'd probably use PK and PM. If I can prove those two sides are congruent, then we have an isosceles triangle. So, to get started, I'm going to go ahead and put all my given information in my proof. We have angle 1 is congruent to angle 3, angle 2 is congruent to angle 4, and PJ is congruent to PO. Now, from here, we need to decide which triangles we're going to use to show congruency. Now, if I look at this, again, our goal is for PK and PM to be congruent. Well, if I choose for this smaller triangle, if I'm going to choose this smaller triangle, then I need to either prove that OM is congruent to JK, or I need to actually prove PK is congruent to PM, which is our goal, so we're probably not going to do that one right away. So, which other triangles can I use? Well, what if I use triangle JKM and triangle OKM? So what if I use these two triangles, JKM and OMK? Let me make sure that I'm naming those right. So if I use those two triangles, well, they share something. They're overlapping. Well, what's overlapping? Segment KM. So we can say KM is congruent to itself. And any time that something's congruent to itself, it's always by the reflexive property. So Km is congruent to Km by the reflexive property. Now from here, I have an angle, this red angle here, in the side. So the only other thing that I need for triangle congruency is either another side or another angle. Well, looking at this, I have angle 1 and angle 2. So I'm going to have a better chance of getting this angle here. So from here, I'm going to go ahead and say that angle JKM is congruent to angle OMK. Those two larger light blue angles. And the reason I can say that is because I have two angles that are congruent, and I'm adding them to two other congruent angles. And so when I add those together, the results should also be congruent. So that'd be the addition property. I'm adding angles together. I'm adding congruent angles together. And the sum of congruent angles are congruent. Now from here, we have enough information to prove that triangle JMK is congruent to triangle OKM. And we can do that by angle, side, angle. Again, that's light blue angle, purple side, red angle. Again, and we can see that on the other triangle as well. Light blue angle, purple side, red angle. So these two triangles are congruent by angle, side, angle. Now, at this point, can I say that PK and PM are congruent? No. Since PK and PM aren't full side lengths of the triangle, I cannot use CPCTC to show that they are congruent. Instead, I can use the full segment. So I can say that segment OK and segment JM are congruent to each other. those are now in orange or yellowish. Now, the reason that we can say that is because if the triangles are congruent, then the corresponding parts of the congruent triangles are also congruent. Now, if we look at this, I have this yellow angle here, this golden angle. What happens, and again, this golden angle is congruent to the other golden angle, and I have these two green angles. What happens if I take the green angle away from the gold angle? Well, I'd be left with PK, and I'd be left with PM. So we can now say that PK is congruent to PM. And the reason for that is because I took away the green angle from the gold angle. So I used subtraction. So it's the subtraction property. I subtracted congruent segments. From here, well, that was our goal. Our goal was to show that these two side lengths were congruent, because if they were, then we can then say that triangle KPM is isosceles. Because if two legs of a triangle are congruent, then the triangle is isosceles. And with that, this proof is finished. So, that will do it for our notes today. Thank you guys so much for watching. If you have any questions, please leave them in the comments section below or contact me. Other than that, have a great rest of your day, guys. Thank you so much for watching.